Welcome to our presentation. My name is Ch-Shih Jao. I would like to introduce my colleague, Austin Parrish, and my academic advisor, Professor Andrei Shkel. We are with MicroSystems Lab at University of California, Irvine. In this presentation, we are discussing SugarQ PLT, which is a real-time pedestrian localization testbed using full multi-IMU, barometer, and ultrasonic sensor. Having a pedestrian localization system can bring many benefits. It can not only enable location-based services in many industries, such as healthcare, entertainment, or retail store, but also increase situation awareness for public safety. Here in MicroSystems Lab, we are focusing on the application for public safety, and we are building pedestrian navigation system for firefighters and first responders. Pedestrian navigation system needs to provide a person's position information in both indoor and outdoor environment. In outdoor environment, position can be obtained by GPS. GPS achieves positioning by trilaterally signal transmitted from satellites. However, in indoor scenario, these signals are very weak, so position information becomes orders of magnitude less accurate. To fill the gap in indoor scenario, several technology has been used as the core for pedestrian navigation system. These technologies include vision-based system, LiDAR, beacon-based solution using Bluetooth and Wi-Fi, cellular-based opportunistic navigation system, and inertial navigation system. However, when it comes to firefighters or first responders application, there are more design requirements for a pedestrian navigation system. It has to work in environment where it has low light intensity. It has to deal with smoke. Installation time needs to be short, so no pre-installation infrastructure can be used. Last but not least, the position information needs to be always available. Under this requirement, inertial navigation system is the only option. Inertial navigation system provides position information based on an inertial measurement unit, or IMU. An IMU consists of 3-axis accelerometer and 3-axis gyroscope. By integrating gyroscope and accelerometers reading, orientation, velocity, and position can be estimated. However, IMU fabricated using micro-electromechanical system, or MEMS technology, has inevitable noise and time varying biases. The noise and the bias in the system leads to a large position error. For example, in a pedestrian navigation task, if we use a consumer-grade IMU and simply implemented inertial navigation system algorithm, estimated position can exceed 100 meters after 1 minute of operation. In pedestrian navigation, an IMU can be mounted on a person's shoe. This configuration can enhance the performance of the inertial navigation system with an algorithm called Zero Velocity Update, or ZUPT. The ZUPT algorithm uses the assumption that velocity of a person's foot is very close to zero when it's on the ground. Under this assumption, velocity errors are periodically calibrated during the stance phase of each step. In practice, the ZUPT AD-INS can be realized in the extended common filter framework, where inertial navigation system is the prediction step. The zero velocity measurement are used in the update step when a stance phase is detected. In an actual mathematical implementation, the ZUPT AD-INS uses state that includes orientation, velocity, and position. In the prediction step, the state in the previous iteration and the current IMU measurement are inputted to the inertial navigation system algorithm to get the current predicted state. In the update step, the velocity error can be measured by subtracting a pseudo measurement of zero velocity with current predicted velocity state. The velocity error multiplied by a common gain are used to calculate the updated state, and velocity estimates in the updated step are calibrated. This navigation algorithm has been demonstrated to have a position error of less than 1 meter after traveling for 1 minute using a consumer-grade IMU. Although ZAP algorithms significantly improve the navigation accuracy, the error can still be unsatisfactory in firefighting scenarios. To further improve the accuracy, different non-inertial sensors are used to augment ZAP ADINS via sensor fusion solution. Many different sensors has been considered for this purpose. And among these sensors, aidings from ultrasonic sensor and barometers have shown promising results. In this research, a downward-facing ultrasonic sensor was used to increase detection accuracy of the stance face detector, which lead to an improved navigation results. In another research, measurements obtained from a barometer were used to estimate absolute vertical displacement, and this information bounded error growth of the ZAP ADINS on vertical axis. The pedestrian navigation testbed used in this research are very flexible and easy to use. However, the system was relatively bulky, so it is not realistic to test the algorithm in other pedestrian navigation scenario. For example, running up and down the stairs for a long time. There are a commercial product that comes in compact solution. Back in 2012, OpenShoe was developed to demonstrate the navigation accuracy based purely on foot mounted IMUs. This product inspired many interesting and useful applications. In UC Irvine MicroSystems lab, we were also inspired by the OpenShoe, and we envisioned that it will be beneficial to have a hardware that is not only compact, so that we can run extensive experiment, but also flexible enough to test state-of-the-art sensor fusion algorithm. Having this goal in mind, we are developing a real-time pedestrian navigation system called SugarCube. This is the SugarCube pedestrian navigation system. What you're seeing here is a prototype, and we are continuing to work on miniaturization of the system. The SugarCube platform has a microcontroller, a Bluetooth, a lithium battery, onboard sensors, including IMUs, consumer-grade IMUs, barometer, and ultrasonic sensor. The specification of the onboard sensors are listed in the table below for your reference. When the system is running, the microcontroller implements a series of operations in real time. The system flow is described as follows. After the system is powered up, it goes into an initialization phase. During this phase, sensor digital communication are initiated and initial bias of the IMU will be estimated and removed. After initialization is done, the system starts collecting measurements from all the onboard sensors. The collected measurements are used are used as inputs to the navigation algorithm, and information such as orientation, velocity, and position will be produced by the microcontroller in this phase. The produced navigation solution are transmitted through Bluetooth or USB to a remote device. Then user have the option to reboot the system or continue with current navigation task. Using this hardware and this system flow, the SugarCube system provides real-time position information for its user. To demonstrate and evaluate the performance of the SugarCube navigation platform, we conducted a series of indoor walking experiments in Engineering Gateway building at UC Irvine. In the experiment, a person wore the SugarCube system on the right foot, and the position outputted from the SugarCube platform are transmitted through Bluetooth to a customized user interface on a laptop. The user interface saves and displays the received information on the Google Map. This plot shows the experimental scenario. In each experiment, the person walked a closed trajectory based on markers on the floor. The trajectory includes terrains of flat plains, ramps, and stairs. The total trajectory length was around 50 meters, and the duration was about 1 minute. This plot shows navigation results in one of the experiments. In this plot, you're seeing a red triangle, a blue trajectory, and a green trajectory. The red triangle indicates the nominal start and ending position. The blue trajectory is a solution generated by the Sugar Cube platform. And the green trajectory is a solution produced by simply implementing inertial navigation system based on IMU measurement. We can see that in this experiment, the green solution produced by inertial navigation system had a displacement error more than 100 meters. In comparison, if we take a closer look at the plot, the blue trajectory produced by Sugar Cube system reduced the error to less than 1 meter. We repeated this experiment 10 times, and this plot shows the 10 estimated destinations, which are marked by the blue crosses. To quantify horizontal position error, we use circular error probable, or the CEP, which encloses 50% of the data. In this plot, the CEP is the blue circle, and it has a radius of 0.76 meter. For position along vertical direction, we use root mean square error, or RMSE. The vertical RMSE of the Sugar Cube was 0.24 meters. With this experiment, we have shown that the position accuracy of the Sugar Cube was less than 1 meter after navigating for 50 meters. In summary, we are developing a pedestrian navigation system for firefighters and first responders. Our approach is to use inertial navigation augmented by zero velocity update algorithm and non-inertial sensor fusion. In order to have a compact hardware that is flexible enough for testing state-of-the-art algorithm, we developed the Sugar Cube pedestrian navigation platform that integrates multiple sensors and produce navigation solution in real time. We have demonstrated that the Sugar Cube had a position error less than 1 meter after traveling for 50 meters. Finally, we would like to thank our funding agency NIST for providing financial assistance for this research. Thank you for attending our presentation.